So hello, everybody. Good morning, or good afternoon, or good evening, depending on the part of the world where you live. I'd like to start briefly introducing myself before entering the topic of this webinar in such a way that if anybody is still connecting, they may join us in these minutes. Well, my name is Davide Fissore. I'm a full professor of chemical engineering at Polytechnic di Torino. Polytechnic di Torino is a university in Italy, in the northwest of Italy. I work in the field of freeze-drying. In particular, I'm interested, I'm active in the field of modeling freeze-drying process, in particular, the development of model useful for process optimization, for process control, for process monitoring, process control for cycle development, cycle optimization, development of new systems for non-invasive monitoring of the freeze-drying process. So this is the general framework of my activity at Polytechnico di Torino. Not just my activity, because here we are in a quite large group with my colleagues Antonello Barresi, Roberto Pisano, and with several PhD candidates, postdoc, master students working on their project. So it's a pleasure for me to be here today and to meet virtually in this moment so many people. I would like to invite you to use the chat for asking questions, because microphone is mute for almost all of you, and so just to avoid switching on, switching off microphone and so on, you may use the chat in every moment when you have questions. If I'm able, I will answer your questions probably during my talk or at the end. Okay. Today, what I'm the main topic of this webinar is MicroFD. So, first questions I would like to pose to the participants is just if you have ever used this equipment, this freeze dryer. I don't know, as any one of you used for process development, for carrying out cycles in its lab, the micro freeze dryer, or is something completely new? Just to also to tune my talk. May use the chat if you want. Well, someone has used it. Okay. Well, it seems that for most participants is something new. So I would like today to give you a framework about the use of this apparatus. About 30 minutes, 35 minutes. I will try to give you some take-home messages in this at the end of this webinar. MicroFD, micro freeze dryer is a freeze dryer. First of all, you may use it to carry out freeze drying cycles in your lab, to investigate the effect of operating conditions of formulation, characteristics, compositions, and so on. And at the end, after the study, you need to transfer this result, this information, to the production freeze dryer. This is what you usually should do in your lab using other freeze dryer, other lab scale freeze dryer or pilot scale yield. But in this case, you may have some specific advantages for this. In this sense, we can move from MicroFD to macro freeze dryer, I mean to large scale unit. But we may do also vice versa. I mean, we can move from macro freeze dryer, from large scale unit, to micro freeze dryer. I mean, we may try to replicate in MicroFD the heating conditions the product will experience in a different type of apparatus. So we will see these two ways for using this equipment. This is MicroFD. As you may see in the picture on the left, is a very small apparatus, is a very small freeze dryer. The chamber shown in the picture on the right may host, well, 7 vials if you are using 20R vials, or like in the case shown in this slide, 19 vials. In this case, 10R vials are loaded in the freeze dryer. You may load even a higher number of vials, obviously in case the vial diameter is smaller. But in any case, the number of vials, the size of the batch that you process is significantly lower than the size of the batch of an industrial scale freeze dryer, or even of a pilot scale unit. The fact that few vials are processed is a very important issue, because it allows at first saving time. Little time is needed for batch preparation, batch loading, batch unloading, for condenser defrosting. All these steps need few time in this case. But which is the most important issue from my point of view, is that this way of carrying out experiments allows to save raw materials, because and this is a critical issue in case the cost of the raw material is high, the availability of raw material is not sufficient to load a pilot scale dryer or an industrial scale one, or even in case the formulation has not been fully developed. So you may use MicroFD for both formulation and process development, like all the other pilot scale unit, okay, with important advantage that you save raw material and that you save time. But there is a second important issue, because obviously when you carry out experiments for process development, what I mean for process development, I mean that you modify, you change the values of shelf temperature, the value of chamber pressure, and you want to see which is the effect of this change, the effect on final product qualities, the effect on duration of the drying stages. Okay, you may do it with a very low amount of raw material. But there is a second important issue that has to be taken into account, and that MicroFD allows you to explore. And it's the problem of process transfer, or process scale up. As I told you before, in all cases, you carry out experiments in a pilot scale unit in your lab, and then you need to move to a manufacturing scale. you need to change something in your process. You need to modify drying duration. You need to modify, to change the value of the operating conditions in such a way that what occurs, what will occur in the manufacturing stage will be the same you have observed at a smaller scale. What you want is that the evolution of product temperature versus time and drying duration are the same in the two freeze dryer. Actually, MicroFD gives you some interesting possibility for minimizing the effort needed to transfer a process, as I will show you in a while. At first, we have to understand why we have a problem of process scale-up, of process transfer. The problem is related to the way heat is transferred to the batch. In a freeze-drying process, basically, we supply heat to the product, and this heat is used for ice sublimation, okay? So the product is something like a closed system in which we introduce heat and we remove it through sublimation. If the rate of heat supply is equal to the rate of heat removal, then we are in a sort of equilibrium. If the rate of heat supply is higher than the rate of heat removal, then we are giving to the product too much heat, and the result is that the temperature increases and may overcome the limit temperature. So the heat transfer to the batch is a key point that has to be considered. This framework, we focus on the paper published by Bernadette Scutellà 5 years ago, more or less, on applied thermal engineering. They investigated the heat flow rate in the so-called central vials, so vials in the central position of the batch, and the heat flow rate in the edge vials, distinguishing between edge vial C, vials that are in contact with the rail, with the metallic frame used for loading and unloading purposes, and edge vial E, that are the edge vials not in contact with the metallic frame. If we have a look at the graph in the right-hand side, we may see that at first there is a different heat flow rate according to the position of the vial in the shelf. Vial in the central position receives a lower amount of heat with respect to vial at the edge of the shelf. First point. Second, vials receive heat from the shelf. They receive heat through conduction in the gas surrounding the vials. They receive heat due to radiation from the rail, from radiation from the top shelf, from chamber walls. Obviously, the heat transferred from the shelf is, it's the same. It's not dependent on the position. Which is dependent on the position is the heat related to radiation, the heat related to conduction, okay? Usually, when people deal with the heat transfer mechanism, the rate of heat transfer to a product in freeze dryer, usually people do not consider the heat flow rate. They consider another parameter, that is the famous KV, the heat transfer coefficient. Let me introduce this parameter. This is a sketch of what is occurring in a vial in a freeze dryer. In the vial, we have a frozen layer, dried layer, moving interface from the top to the bottom of the product. We have heat flux from the bottom, from the heating shelf, heat transfer due to radiation, conduction, and so on. All the heat transfer mechanisms that were evidenced by Bernadette in her paper. Actually, people use always this equation. In this equation, we say that all the heat transferred to the product is given, is written, is calculated, is expressed as a product. A product by the difference between the temperature of the heating fluid and the temperature of the product at the bottom of the vial. This is called the driving force. And this driving force is multiplied by the heat transfer coefficient, by the overall heat transfer coefficient. Obviously, if we have a look at, or we focus on the edge vials or on the central vials, the difference T fluid minus Tb is more or less the same. But as JQ, as the heat flux to the product is different, then the result is that KV is different. Okay, KV for edge vials is different with respect to KV of central vials. So usually people, instead of using this kind of representation, so clearly expressing the heat flow rate, usually people in freestyle domain talk about KV. They are exactly the same because KV is multiplied by this difference. T fluid is usually known. Tb may be measured quite easily. And so from KV, you may get the value of the heat flux. But it is important because we will talk about KV in the different unit, MicroFD and the larger scale apparatus. First point, the heat transfer is not dependent on the product being processed. Talking about heat transfer, we talked about the radiation from the rail, radiation from channel walls, conduction in the gas, about the heating fluid. Okay, we am not talking about the product inside the vial. We may carry out experiments with water and sugar, with water and active pharmaceutical ingredient. But if we are investigating the rate of heat transfer, so KV, the value of KV is not dependent at all on the product being processed. First important concept. Second, heat transfer is dependent obviously on vial type, on vial position, on the freeze dryer, because all these elements affect the rate of heat transfer to the product. And if you want to get the value of KV, the only way you have to get a detailed picture of your system is to carry out a so-called gravimetric test. You run a cycle in ice sublimation test for 3 hours, 4 hours, 5 hours, something like that. And you measure the weight loss delta M in all vials. You multiply this delta M by the entity of sublimation. You divide this product by the area of your vial and by the temperature difference. So you need to measure not just the weight loss, but also the temperature in some vials. By this way, you get KV, and you get a detailed picture of KV in your batch, like the one shown in the right-hand side of this slide, with a higher value of KV at the edges of the shelf and a lower value in the central part. What about MicroFD? This is what you may get in your pilot scale unit or even in an industrial scale unit, running one test with just water. You don't need any active pharmaceutical ingredient to carry out this test. In MicroFD, the situation is slightly different because in MicroFD, you have your batch of vials, 19, 7, it depends on the size of these vials, and the vials are surrounded by an aluminum ring. The temperature of this aluminum ring may be manipulated. You may independently on the temperature of the heating shelf. I mean, you may set the temperature of this ring to be equal to the temperature of the heating shelf or to a different value. There is the possibility to select what is called offset. I mean, you measure the temperature in some vials of the batch, putting thermocouples inside, and the temperature of this aluminum ring is set on the basis of the temperature of the product. So it's given by the temperature of the product plus minus the offset. It depends if you have selected a positive offset or a negative offset. This is an important degree of freedom that you have. Why? Because by manipulating the temperature of the aluminum ring, you manipulate, you affect the amount of heat that is given by the equipment to the vials that you are processing in MicroFD. And by this way, you may replicate, you may reproduce what? Well, in principle, the row of the aluminum ring, may replicate a row of vial. In this way, if you set properly the temperature of the aluminum ring, the dynamics that you are investigating in MicroFD will be the dynamics of the vials in central position in the larger scale equipment. This is useful for which reason? Well, first, obviously, central vials, the so-called central vials, represent the majority of the vials of a batch. The drying time is related to the velocity of drying in the central vials. But in principle, you may tune in a different way the ring temperature to heat more the vials in this batch to replicate in MicroFD the dynamics of the edge vials of your larger scale unit. This is important. Why? Well, because obviously edge vials are characterized by the higher temperature. So if you want to be sure that no collapse, no shrinkage occurs in your large unit, this type of study is what you have to do. So if you want to move from macro freeze dryer, large scale unit, to MicroFD, what you need to do? At first, you need to identify in the larger scale unit the group of vials of interest. At first, you want to investigate what will occur in central vials because you are interested in evaluating dry length, duration, you are focusing on the majority of the batch and so on. Or you are interested in the edge vials because they are the hottest in your batch. This is the first point. And you need to carry out the characterization, the gravimetric test in the larger scale unit. But it's a test that you carry out once in your life with the specific type of vials that you will use. It's a gravimetric test. It lasts a few hours. It just needs water for injection, and no more than this. Then you move to MicroFD, the sense from macro to MicroFD. And in MicroFD, you need to identify which is the highest temperature offset to mimic the target group of vials to have the same heat exchange rate. This is a paper published by Goldman in 3 years ago, more or less. In graph A, you see a map, a color map, showing the value of KD in a larger unit. In B, you may see a color map, KD values obtained in MicroFD, modifying just the temperature of the ring. What you see? You may see that if you select an offset plus 3, in your MicroFD, you replicate the heating condition of the first row vials. If you select a lysine temperature offset -5, you replicate in your MicroFD the evolution of the product in the central vials. This is just dependent on the heat transfer rate. it does not depend at all on the formulation being processed. So you may carry out this test once in the life using water for injection, water, distilled water in your vials. You get these infos, and then you may use these infos. So you select the temperature offset, and you will be sure that your MicroFD will behave like the central vials of a larger unit or like the external vials of the larger unit. So besides providing significant time saving and raw material saving, it gives you the flexibility to replicate this type of dynamics. But you have also another possibility. You may, in the previous slide, I was talking about moving from larger scale unit to a smaller one. So I want to replicate in micro what will occur in a larger apparatus. We can use a different approach. I mean, I carry out a test in MicroFD without paying attention to the temperature of lyocene. I want to save time even from this point of view. I don't want to carry out this characterization and so on. So just one test. And I want to use the result I will get for process scale up, for process transfer. Is it possible to do this or not? Well, let's see an example. Here is a picture of MicroFD that is in my lab, 19 vials in this configuration, 10R. And in the right-hand side, you find a sketch of this batch. Why I'm showing you this sketch? Because it's quite meaningful. I mean, if you have a look at vial 19, the vial in the center of the batch, this vial is surrounded by 6 other vials. If you have a look at vials numbered 13, 14, 15, 16, 17, 18, and stop with 18, you have that all these 6 vials are again surrounded by other 6 vials. So these 7 vials in the central part of the batch receive heat from the bottom and receive heat from 6 vials surrounding them. The situation is a little bit different from the external vials, the vials in contact with the lyocene, because in this case, each vial is surrounded by 3 or 4 vials is in contact with the lyocene. So the situation is a little bit different. But we may again make some modeling of this system. So we may group central vials into what is called in this slide as layer 2, the other vials in layer 1. Vials in layer 2 receives heat from the shelf, from the other vials of the batch, and there is a heat leaving these vials related to ice sublimation. If we focus on layer 1, vials of layer 1 receives heat from the shelf, exchanges heat with layer 2 and with the lyocene, and they lose heat due to sublimation. Here you add 7 and 12 because there are 7 vials in layer 2 and 12 vials in layer 1. So what is occurring in one vial has to be multiplied by 7 or by 12 to account for this. The key point is that the KV coefficient describing the heat transfer from the shelf to the vial in the layer, in the freeze layer, is the same for layer 1 and layer 2. It's exactly the same of the paper of Bernadette Scutellin, in which the heat flow rate from the shelf was always the same, independent of the position of the vial over the shelf. And is always independent on the dryer size, on the dryer characteristics. It is always the same KV. K12, I mean the heat transfer coefficient due to vial contact. Also this is the same for all vials of layer 2 and is expected to be the same even in a larger scale unit. What is different is the KL, obviously, in this case. So, what kind of test you need to carry out? Well, in principle, if you have in mind this picture, what you have to think is this. I carry out a test. I measure the weight loss in vials, in all the 19 vials. It takes a few minutes measuring this weight loss in all the vials. I measure the temperature of the shelf, Ts, and the temperature of a few vials in group 1 and in group 2, T1 and T2. TL is obviously known as the temperature of glycine. So I have a series of variables that are measured, and I may use these measured variables to estimate the value of KV, K12, and KL. Is something similar to what, I don't know if you have ever carried out the pressurized test, or you have any experience with pressurized test, MTM, with this type of software and of algorithm. In that case, a pressure rise is forced in the machine. Then there is a mathematical model with some unknown parameters, and the values of these parameters is estimated looking for best fit between calculated and measured values of pressure rise. Here is exactly the same. Here we measure the temperature in the vial. We have a mathematical model used to calculate the temperature emission, and the software that looks for the best value of KV, K12 in order to get this best fit. Here is an example of results. 10 are vials processed in a vivo freestyle pilot scale unit. 14.4 is the value of KV. I carry out the test in MicroFD without paying attention to isolate temperature. I set it equal to shelf temperature. No problem at all. I measure the temperature, measure the weight loss. I use a model. I'm not giving you some details about that because they are not so easy, but anyway, it's a software, black box, okay? And I look for the value of KV that provides best value between calculated and measured value of temperature. And the agreement is shown in this graph. The value of KV I obtain is very close to the value obtained in vivo. Here is an example of results at 100 millitories chamber pressure, a different one. Also in this case, very good agreement between modeling and measurement, and satisfactory agreement with respect to KV. So I have the possibility, if I focus on heat transfer, to use MicroFD in two ways. From macro freestyle to MicroFD, I use information obtained in a larger scale unit to replicate in MicroFD the target group of vials. And so I may develop my process taking into account what the product will experience in the different units. Or I may carry out a test, a gravimetric test again, in MicroFD without paying too much attention to IC temperature, and I may use these results moving for scale-up purposes. I estimate in MicroFD the value of KV that will be obtained in the larger apparatus. What about mass transfer? With respect to mass transfer, we have again to focus on the equation that is used to describe this mass transfer. The equation that you probably know is the one I'm showing to you. I mean, the mass flux from the vial to the chamber is again given by a product between a parameter, in this case RP, so-called resistance of the product, and a driving force. Driving force here is the difference between water vapor partial pressure at the interface of sublimation and in the chamber. Also in this case, this driving force is known. Water vapor partial pressure in the chamber is equal to chamber pressure, for sure. And water vapor partial pressure at the interface of sublimation is a well-known function of product temperature. So this driving force is known like T fluid minus TB in JQ equation. So if we know RP, we are able to characterize mass transfer from formulation to the equipment. Key point is that mass transfer is not dependent on vial type, vial position on the equipment, provided that the same freezing path is used. So if I am using controlled inoculation at a certain temperature in the equipment, I have to use the same controlled inoculation technique at the same temperature in the other one, for sure, okay? But if the same freezing path is used and no collapse or shrinkage occurs, then RP is the same, okay? Obviously, when we look for a freeze-drying cycle, we would like to avoid a shrinkage collapse. So it's quite easy to get the same RP in different freeze drying. RP, you probably have seen this equation. There are two parameters, A, B, and a third parameter, RP0. In which way I can use MicroFD to get this parameter? Well, in this case, the story is a little bit more complex from a theoretical point of view, but then from point of view of the calculations needed is very simple. So I hope, even if we are close to the end of this webinar, you may still follow me in this few equation. Unfortunately, I'm an engineer, and sometimes an equation should appear in my presentation. So, but they are very, very few. The starting point is that the equation, this one, expressing the sublimation flow rate, actually is the equation used in freeze-drying domain. Everybody in freeze-drying talk about RP, but actually is a version, a particular version for freeze-drying practitioners of a more general law that is the Fick's law, the law of Fick. According to the Fick's law, the first Fick's law, sublimation, the water vapor flow rate is written in this way: molecular weight of water, effective diffusivity, ideal gas constant, temperature, driving force, and the thickness of the dried layer. This equation and this one are exactly the same, provided that RP is written in this way. So RP is actually not just RP0, A, B, okay, but RP is a very specific theoretical background. Is ideal gas constant by temperature divided by molecular weight, effective diffusivity, and thickness of the dried layer. Effective diffusivity is given by the Knudsen diffusivity multiplied by cake porosity divided by cake tortuosity. And the Knudsen diffusivity is a function of the mean pore size, RE, and of temperature at the power of 0.5. So if we replace dk into the equation expressing the effective diffusivity, we get this. And then we replace this into the previous equation expressing RP. And we get this complex, quite strange equation. A complex equation, there is still one step that has to be done. What about pore size and tortuosity? Usually, pore size and tortuosity are written as a function of layer thickness in this way, with the two parameters, A0 and A1. If we replace RE divided by 2 into this equation, we get something that is equal to the A by A drive divided by 1 plus B A drive, where A and B are written in this way. So we may express RP, so the resistance of the cake, either using A and B or using A0 and A1. But they are not the same. I mean, A0 and A1 are two parameters related to the structure of your product. A and B are two fitting parameters that are related to the structure of your product, A0 and A1, but also to the temperature of your product, even if at the power of 0.5, but they are dependent on that. Okay, so A0 and A1 are the two parameters that are independent on the equipment, on the thermal history of your product, not A and B. So you carry out a test in your MicroFD, you get RP versus L dried. There is a nice software that provides immediately you these results. You from RP versus L dried, you have to extract this information. You get A and B by means of fitting, and from A and B, you get A0 and A1. These two parameters may be used for process transfer. Let me show you an example. Here, I was carrying out a cycle, a very simple cycle, 5% super solution, 100 milliliter, minus 10 Celsius, spontaneous circulation, in Rivo, pilot scale unit, and in MicroFD. MicroFD, I was not at that time concerned about the temperature of Lyosim. I said, okay, temperature of Lyosim is equal to shelf temperature, and let's go on. Obviously, if I look at the Pirani over Barton pressure ratio versus time, I may see that what is occurring in MicroFD is different from what is occurring in Rivo. Drying time is different. Drying time is, well, the inflection point of this curve, or in some cases is considered to be the onset or the offset, where there are for sure at the offset. I mean, when the difference between the Pirani and Barton pressure is very small, you may say that drying is ended. And you may see that in this case, in MicroFD, drying is longer than in Rivo. So, in which way can I transfer the results obtained in micro to the other apparatus? Well, in the test, I have a temperature measurement. And here you may see temperature measurement in Rivo and temperature measurement in MicroFD. And they are different because, well, I was not concerned about replicating in MicroFD the dynamics of the larger unit. Here, the point of view is from micro to macro, okay? You may see in all cases I'm below minus 32, no collapse, no shrinkage at all, and so on. And here is the result, the cake structure. Here is the trend of RP or RE over 2, so parameters A0 and A1, I obtained in MicroFD and in Rivo. They are almost coincident. So in the two equipment, the temperature was different, drying time was different, but if I carefully use, I properly use the experimental data, I get something very, very useful. So, which are the take-home message? The question you probably have is, how can I transfer data about a freeze-drying process obtained in MicroFD to a different freeze dryer? You have two possibilities. The first one, this is the one probably more established. There are some papers about that, even some papers from my group, is to replicate in MicroFD the dynamics of the other equipment. You do not have, MicroFD provides a very high flexibility in this framework. Once you have done your characterization, you may play as you want with the driver. But you may do also your job in a different way, some way, in a more traditional way. I mean, you carry out your experiment in MicroFD. From one test, gravimetric test, you may estimate the value of KV, expressing the heat transfer from the shelf to the product in the vials. And from one test with the product, in this case, you may get the two parameters, A0 and A1, that describe the structure of your product cake that you want to be the same in the other unit, because obviously you want to avoid collapse or shrinkage. So you have these two approaches that may be used for effectively for solving in an original and effective way the problem of process transfer and scale up in this unit. In the end, I would like to acknowledge my team at Polytechnic di Torino. These are the guys and girls that worked in this field recently. Is part of the lab research team of Pore, the part involved in MicroFD, and as well as Mirror Technology, and then Pharmatech, the Italian branch, because they have been solving various issues related to the machine, and they strongly supported my job and my experiment with the tool. And obviously, I would like to acknowledge all of you for your attention. And I would like also to invite you to ask questions or curiosity about what you have seen in this webinar. Thank you.
Thank you so much, David. Please feel free to type questions into the chat box.
There is. I would like to start with the last sentence in the chat where Elite said that she used the MicroFD for human tissue graft. Actually, in this talk, I always talked about vials, product in vials, but obviously you may process in your MicroFD the product you prefer. Okay, it's a freeze dryer, a small one. What is just to complete the previous point. So it's a small freeze dryer, few raw material, few time, and gone with your test. Well, the point is this. Well, T is the temperature of your product. Okay. The problem is that when you carry out a test in MicroFD or in Beta, in Vivo, wherever you want, you cannot be sure that the temperature of the product is the same you would like, obviously, but you cannot be sure that it's perfectly the same, particularly when you're still developing your cycle. Okay, so this is the first point. Epsilon is the void fraction of your cake that is correspondent to 1 minus solid percentage of your formulation. So if you have a solid fraction 5%, epsilon is 0.95. K is the Knudsen constant, so it's a number, 22.9 if I'm not wrong, but it depends on the measurement number, on the measurement units. Is a number that is well known. What is unknown? Totally unknown is the cake structure. What is totally unknown is the ratio RE, mean pore size radius, over 2. This is unknown. The theoretical assumption is that RE over 2 is equal to A0 plus A1 by L dry. But in this way, we are just moving the problem. I mean, we don't know RE over 2, then we don't know A0 and A1. But we need to get A0 and A1 because they are the same in different type of apparatus, because they are the parameters related to the structure of the cake. Okay, in which way we get it? Actually, what we do is, one, we estimate RP versus L dried. Okay, I will go on this point in a while, but at first the structure of the algorithm. At first, I get RP versus L dried. Then, once I have the curve RP versus L dried, by means of best fit, I get A and B. Okay, best fit, A and B. Then, from A, I may calculate A0, and from B, I get A1, because A0 was obtained from A. Okay, so I start from the traditional curve RP versus L dried, estimation of A and B. RP0 is just a fitting parameters, it can be deleted, it's not necessary actually. And from A and B, I get A0 and A1 that may be considered to be the same in different equipment. RP versus A dried, well, is given by the software of MicroFD. If I don't trust the software, I may do this calculation using Excel, because using this equation. So I know KV, I know chef temperature, product temperature, chamber pressure, and so on. And so I may calculate this curve. Okay, so this is a different way to express the resistance of the cake. Instead of RP, at the beginning of my job, I always talked about RP, calculated RP, and so on. But actually, when we move in different equipment, it's better to use this A0 and A1 that are fitting parameters. No more than this. If your product is a uniform cake structure, for example, for mannitol products, if you consider a product with like sucrose, where the dependence of the resistance is as the typical asymptotic behavior, okay, it means that A0 is significantly higher than A1, okay, and you will get an almost flat curve, reflecting that there is a layer at the beginning of the cake with small pore radius that is responsible for most of the resistance, and then even if we increase the thickness of the cake, this does not reflect in a significant increase of the resistance. This is the explanation for the asymptotic trend. But anyway, it is obtained by this analysis. Patricia, can MicroFD be obtained, be used for double chamber systems? Why not? Again, it depends on the goal that you want to get. I mean, MicroFD is first of all a small scale freestyler. you process few vials, small amount of tissues, you process dual chamber cartridges or whatever you want in a low amount, with the possibility, with an additional degree of freedom that you do not have in other units. That is the temperature of this ring. Okay, so again, you may use it from macro to micro FD. So if you have done this characterization of the transfer rate, you may play in your MicroFD trying to mimic the evolution of the other unit, or on the other way, you carry out your test in MicroFD with the dual chamber system. I never used it, to tell you the truth, but anyway, there are no reason for expecting any type of problems. I have in my lab 3 freeze dryer actually. I have a couple of pilot scale freeze dryer and a micro freeze dryer that, well, sometimes I use it for process development. For example, I was working recently on formulation of nanoparticles for delivering mRNA for a pharma application, and it was necessary to assess the composition and the type of the formulation, cryoprotectants, and so on, and obviously the amount of nanoparticles. I was working with solid lipidic nanoparticles and also liposomes, and I did not have any large amount of samples, so micro was very useful. In other cases, I use the equipment for developing cycles and doing process transfer. For the price, I guess the best you can do is to talk with the commercial division by Miracles, because the price changes with time. I have this unit in my lab since 4 years ago, more or less. And so the situation now may be different. Okay, you may also use some Rayo beads. Rayo beads is a technology that appeared on the market some months ago, or few years ago. Very promising for getting accelerated freeze drying cycles, as you are freeze drying small particles and not thick layers of frozen particles or frozen material. In some cases, these beads can be put inside vials, so no difference from the story I told you before. In other cases, you may think working with a tray. Actually, this could be an input for Miroc. I don't know if they have something like that in production, but in principle, I do not see any reason for preventing the use of a tray inside the MicroFD for processing this type of product. You may put in the tray the human tissues, or you may put beads or any type of other products. Okay. Anyway, if you are scared by these equations, don't be scared about them, because all these details are hidden by the software of the machine, and so you may just take your result. If you want to do something different from the machine, you get all measurement you want, temperature, pressure, and so on. And you may write your own script in Python, MATLAB, Excel, whatever you want, and do any type of post-processing. It depends on the goal of your job, or your background, or your curiosity. So the possibility exists. Okay, we exploited this possibility, but because actually we are a research university, so I was interested in the use of these for developing scale-up strategies, for mathematical investigation, and so on. And so in some cases, I took the numbers from the machine and I used them on my laptop, not just stopping myself in front of the result of the software. But it depends on the goal of the job. Okay. Don't know if you have any. Well, the only issue related to the use of trace, bits, and so on is the stoppering, because the machine has the stoppering device that is okay. Obviously for wires, you have to pay attention when you introduce inside something that has not to be stoppered. Okay, it's the only concern that you may have. Then you have the usual condenser, vacuum pump, refrigeration system. So all the elements of the freeze dryer. So Brian, I don't know if.
Okay. Thank you so much, David. Yeah, it looks like the questions have slowed down a bit, and we still have people here. And what we can do is follow up with everyone as we get some slides and things like that available to you. And it was just a great presentation, David. Did you have any more closing words? Thank you so much. It was really an excellent presentation.
Thank you, Brian. Well, actually, the closing remark I have always in all these meetings or conferences is that from this machine you may get really a lot of information. You may use it at let me say basic level, like a freeze dryer, okay, as an alternative. Saving raw material, blah blah blah. Okay, it's another machine for your lab. Okay, but it's expensive. Also, the other freeze dryer are expensive. So I don't think it's much more expensive than other pilot scale or upscale unit at first. But at second, as the machine has great flexibility. As very nice software, you may really use it for getting more information. So not just a cycle that works, but a cycle that makes you sure to get a good product at the end of manufacturing in a small time. Because several times I'm involved by pharma company because they have very long cycles. They have problem with process transfer, process scale up, and they do not have the possibility to run in the lab the test that will allow to solve this issue. And to solve this issue in a small time, you don't need a month for doing this, and it is a pity. With this, with this equipment, you may really get more information and go ahead with your process. My final message. Okay.
Thank you so much, David. Very true. So we're available to you if you'd like to learn more about the MicroFD. We'll follow up with you all by email. And everyone have a pleasant day. Thank you so much for joining us today.
Thank you, Brian, and thank you all.
Thank you again, David. Have a great day, everyone.
Bye-bye. Have a good day.